Hello everyone, welcome to my video. This is my final design project at UNISA. I've made a diagnostic tool for the company I work for. Before I demonstrate to you how it works, I would first like to explain to you what we do in the company. We manufacture and build and sell these scanners which is next to me. These we install in grain silos or even outside stockpiles. We measure then the inventory by taking points on the stockpile and then doing a 3D mapping in software. The biggest thing for the need of this diagnostic tool is to eliminate human error when doing fault finding, and also to speed up the process and prevent any unnecessary removal of the instruments. What I've done is I've also created it to be wireless and to work with a cell phone for ease of access. Then technician doesn't need to take up a laptop to the silo when we're walking up the stairs. The plan is for when a technician arrives on site, he can just plug out the current equipment on site and then just plug the wires directly into this box with the same DB9 terminals that we use on site. We also will make use of the site power. If we cannot communicate with the scanner and the power is the reason behind it, we will immediately see that, because then the diagnostic tool will not power up. Let me demonstrate to you how this whole thing works. When a technician arrives on site, you would normally find a box like this one. Then all he has to do is plug out those 3 DB9 terminals on the right hand side, and also the power, which is already plugged out. After removing the current equipment and installing this diagnostic tool, the technician can then just switch on the power of the 3 devices, and then also for the diagnostic tool itself to power on. The 3 devices that I'm referring to is, on this scanning device we've got a laser, which is the blue one. Then also the top part is the pan motor, and then this black tube over here contains the tilt motor. We'll now start a test on the laser. Then we must first connect the Bluetooth before we can communicate with the diagnostic tool. During the laser test, the LED will light up yellow on the diagnostic tool itself, and then after it's done, it will go green, as you can see there. Let's just go back to the test. Here you can see the communication success, the serial number, the distance measurement it took from the laser, and also the laser temperature. After this test was complete, we got the green LED. I will now just switch off the laser power, which then when we run a test again it will fail, and I will show you how it gives us the red LED. Testing for communication now, and it failed, and as you can see it shows me comms failed on everything, and there's our red LED on the laser side. Let's now test the tilt motor. First testing for communication. If that is successful, it will go on and test the other things, which is the home angle. It will look for a stop, a physical stop. Then it will set that position to 0, and now it will look for a maximum stop in the other direction. It will then determine the angle between these 0 and maximum points and give us the range. Also the temperature is given. Let's test the pan motor now. It's exactly the same as the tilt motor. First it's checking for communication, then it's finding the serial number, then after that it's performing the homing routine. Now it's setting that to 0 and looking for the maximum stop on the other side. While it's doing that, it is then calculating the degrees between these two and giving us the maximum range and also the temperature at the end. As this is now successful, the pan motor light will go green. Let's simulate a failure on the pan motor. As soon as I test the motor, the RGB LED will go yellow, stating that it's busy testing, and then if it's failed, it will go red. We're just plugging out a wire and testing that motor. There it's failed and the LED turned red, as you can see. These are my presentation slides. The first one just shows you the scanner and then where it's installed in a normal environment. That would be a grain silo, and then it takes points on the profile and then makes a 3D mapping for you and displays the profile in software, as you can see at the back there. And then also on the second slide I'll show you the device with the hardware. Like I said, the laser with the tilt motor and then the pan motor. Then when a technician arrives, he will see the control box. When he opens, it will look like this. We will then pull out this plug, which is a 24 volts DC power. I've got a plug like this one on the diagnostic tool. Then we'll just plug directly into my diagnostic tool and bypass this moxa. And then also if there's power problems, we will immediately detect it, as the diagnostic tool will not power up. That helps with the fault finding. And this 24 volts DC is then stepped down by a buck converter in my Arduino board, which I soldered on there, and it's converted to 12 volts to power up my Arduino. And then these are the three communication lines with the serial ports, which is the laser first at the bottom, then the tilt motor, and then the pan motor. On the next slide, this is what a site looks like. I've just got an example of two silos here. The control box we talked about is this blue block over here. You can't see very nicely now. And then the main reason for this diagnostic tool is to eliminate everything from this control box back the whole site, where you can just pinpoint does the scanner have a fault on it or not. And then that saves a lot of time for fault finding, to go through wireless radios and then a PC as well, and then a switch and a power supply unit. All of that is eliminated by using this diagnostic tool, just to plug in directly to the scanners. Then this is my block diagram. As explained, this is the LM2596 DC buck converter, which steps down the 24 to 12 volt for the Arduino to work. And then thereby we're making use of the site power and not unreliable power like a battery, which can go flat as well. Then this is the mobile phone, like you can see with the application that I've written. And then also the three RGB LEDs, which lights up the color that we want in a success or failure state. Then these are the three MAX 233s that I'm using to convert the RS232 communication from the device. As the Arduino cannot talk RS232, it uses a TTL communication, and then we convert that to TTL with this MAX 233 chips. Just move this laser. On this fifth slide, you can see the flow diagram. This is quite a lengthy process. We've already gone through all of that. The three blue blocks are your start buttons, which you press if you want to start the test on a laser or maybe the pan motor or the tilt motor. And then these orange circles are the end of the process. As you can see, it flows through, and then on a failure we will get the red LEDs for each one. Also during the test there will be a yellow LED, and then after a successful test there's a green LED that lights up in the hardware. I won't go into detail with this because we've already demonstrated the whole program. This is also on the final slide my circuit diagram. It's not very visible with the yellow and orange, but this small block here, this black block you can see here, This is my board that plugs on top of the Arduino. I've bought this board as a prototype board, and then I've soldered on my MAX232 chips. Both of them are dual chips, so I can run two RS232 lines through this one and two through that one. Only because we're having three devices, we will run two through one of them and one through the other one. These are my three LEDs, which is the RGB LEDs. Then this is also the Bluetooth module, which is an HM10. And then these are the DB9 plugs, which is this is all internal to the box. And then these wiring you can see here is externally wired into the box, as I've explained and demonstrated as well. Then we need the two capacitors for the two MAX233 chips to work. And as I said, this board is my development board. The lines can cross outside of it because these are not soldered, it is just loose wires. On the board it's soldered directly in the straight lines and not crossing each other, and I've got a dual layer which is on top. I've got lines which can cross because at the bottom the other lines are soldered and installed. This then plugs on directly to the Arduino board as mentioned. Alright, thank you guys for watching my video. I know it was long, I'm sorry for that. Also, I just want to make use, before I say goodbye, of this opportunity to thank Professor Pierre Hartog from Free State. Thank you, Professor, for guiding us through this project. It's been a journey and I've enjoyed it. And also one of my colleagues, Dr. Michael Dorfling, who is our software developer. He helped me with the 14-page sketch that I needed to program, and then also was my mentor during this process with programming, where I've learned a lot. Thank you to those two people. Bye bye.